Welcome back. And today we will be seeing the problem Jump Game 2. This is actually very similar to the previous problem we solved, that is the jump game. Now let's first see what this problem says. Okay, in this problem we will be starting at the 0th position and we have to say what is the minimum number of steps that are required to reach the end. In the last problem, we were just checking whether we could reach the end or not. In this problem, we are checking the minimum number of jumps that are required to reach the end. Sounds complicated, right? But we will be using dynamic programming again to solve this problem. And it is also given that it is guaranteed that we will be reaching the end. So we will be having one less thing to worry about. So now let's directly dive into the approach that we will be using. So let's see why we are using dynamic programming in this problem. Because if we are at the position 0, it means we are having two decisions. Okay, so either we could reach 3 or 1. From 3 also we could reach 1. So it means that this is the overlapping problem. And recursion in this particular problem is really very expensive and it is really unnecessary to do that. So let's maintain a data structure named DP. Okay. Now in this data structure, we will be storing the minimum number of jumps that are required to reach the particular position. Okay, this much is understood. Now let's first think about the base case first. We will be starting at the 0th position. Okay, we will always be here. So what is the minimum number of jumps required here? That will be always 0. So we will directly put 0 in our first position. And in every dynamic programming problem, it is really very important to find out the base cases. So in this case, we know that is 0 and this is the base case. Now, when we will code, we will do one thing. We will mark all the indexes as infinity first in this DP. And what will be the length of this DP? The length of this DP will be the length of this array currently. Now let's quickly do that here also, so it will be good to visualize. Infinity, 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 and one more infinity. Okay, so now let's see what are the minimum steps required to reach 3. How will we do that? What is currently present for 3? Infinity. Now, if we are starting at 2, what is the minimum number of jump to reach 3? That is 1 plus minimum number of jumps required to reach 2. Okay, so we will always be making one jump from 2 to reach 3, at least one jump. So, how many jumps are required to reach 2? How we will know that? That is stored in our DP. Okay, what is that value? 0 means 1 plus dp of 0, that is equal to 1. So is this minimum than what is currently stored here? Yes. Then we will strike this out and mark it as 1. Okay, great. Now, is there any element remaining that we could check? No, no element is remaining. So we will move on to the next one. Now we will move on to the 1. Okay, so we will start at 2 again. How many steps are required to reach 1? Let's see. Can we reach 1? 0 plus 2 is, what is the index? Index is 2 and we could reach here via 2. So yes, we could reach. So we will be requiring one jump plus the minimum number of jumps that are required to reach 2. That is 0. So this is 0. So we require only one jump to reach 1 also. So is that less than infinity? Of course it is less than infinity. So we will strike this and mark it as 1. Now let's calculate for 3 also. So how many jumps are required to reach 1 from 3? That will be 1 plus dp of 1, the minimum number of steps that are required to reach 3. So what is that? That is 1. 1 plus 1 is 2. Oh, but we have already stored the minimum and 2 is greater than 1. So we will not update this. Okay. So now let's move ahead. Now we are here. So what are the minimum steps to reach here? We will check from 2. 2, we cannot reach this index from 2. So we will not even update anything. Now we will check from 3. Can we reach this index from 3? Yes, we can. Why? Because what is this index? 1 plus 4 is greater than 3. Sorry, 1 plus 3 is greater than 3. I'm sorry. So we could reach here. So now we will try to update. How many jumps are required? 1 plus dp of 1. And what is that? That will be 2. So 2 is less than infinity. So we will update this as 2. Now let's check from 1. How many steps are required? First of all, can we reach here? Yes, we can reach here in this case. And then how many steps are required? That will be 1 plus 1. That is again 2. And 2 is already present. So we will not update that. Now let's check for 4. Okay. We will see for 2. We cannot reach 4 via 2. So we will not do anything. But we could reach 4 from 3 because 1 plus 3 is equal to its index and its index is also 4. So we have to update, means we will see we could update or not. Means 1 plus dp of 1 and that will be 2. Okay, we'll update this. We will mark this as 2. Now let's check for 1. We cannot reach 4 from 1. Okay, so we will not do anything. Can we reach 4 from this index? Yes, we can. So what are the minimum steps? That will be 1 plus dp of 3 and that is equals to 3. But is 3 less than 2? No, then we will not be updating this. So in the end, whatever the number that is stored in this position, that will be our answer. So we will just be returning dp of what is that 4 and this is the answer. Okay, I hope you have all understood the algorithm. Now let's quickly code that up. This is the function that is given to us. So now let's think about the base case. If the length of the array is 1 itself, so that means we are currently at the last position. So we don't have to do anything, we will just return 0. Okay. Now it is guaranteed that we could reach the end. So we don't have to even check for anything. Now let's make our DP. And what will be the type? It will be of type int. Okay. Let's quickly make that DP and that will be of nums dot length size. Okay. So now we know one thing, that we need 0 jumps to reach the 0th index. So let's mark that. And before marking that, what we will be doing is we will be marking everything as infinity in this DP first. Okay. And how will we do that? Integer dot max value. Okay. We have done this. Now what is the next step I said? We have to mark the 0th position as 0 because we know that we are at the 0th position, so we don't require any jumps. Okay, we have done this. Now what we have to do is we have to check for the remaining number of elements, how many minimum steps are required. So now let's check for the first one. We will be starting at the first position and we will go till the end. That will be nums dot length and I plus plus. Okay. Now we have to check whether we could jump from the previous elements or not. And what are all the previous elements? That will be starting from the 0th position and that will go till I. So this is the case. Now let's see. First of all, we have to see whether that element is reachable or not. How will we check that? If j plus nums of j is greater than or equal to I, that means this position is reachable. Now, what we have to do is if the jumps that are calculated from this position is less than the currently what is present in the DP, then we should update. I could have phrased it better, but okay, let's see. If we will only update DP of I like this. If whatever the minimum is present, we will take that. And what is the next one? 1 plus dp of j. We have already calculated dp of j. So whatever the minimum is there, we will just update that in our dp. And believe it or not, this is the entire code. We just have to return the result. And what position are we trying to reach? We are trying to reach the last position. So we will be returning the last position from here. Now let's run and see whether it is running or not. Okay, it is running. Oh, cannot find the, oh, I'm sorry. This should be of type int. Now let's check again. And it is running. So let's submit and see. As you can see, we have actually solved this problem using dynamic programming, and we will talk about the more optimized solution that will be the greedy approach in the next video. Thank you everyone. If you find this video helpful, please give it a like. It really helps the channel a lot. Thank you.